Well, the first sort of theme that we've treated is that groups are everywhere. We've defined these things abstractly, but really they're very, very concrete. If you're ever trying to figure out what should be true in general of a group, you have a lot of great examples to look at to test your ideas on. So for instance, one of our first examples was GLN-R. Another example we saw was the symmetric group on n letters. And a third example we saw was the group of integers under addition. So when I just write z, I really mean integers with addition. And another of the themes that we hinted at but haven't treated in detail so far is that these things arise as the structure-preserving bijections of something. So what are the structure-preserving things here? Well, this is the structure-preserving bijections for our n with its linear structure. This is just the set of structure-preserving bijections on a set of n elements with just its set structure, no additional structure. And z, there are a lot of ways of sort of realizing z as the symmetries of something. So another sort of thing that we'll be talking about is symmetries of geometric objects. So this is just a hint of something that I'm not going to treat in detail now, but which will be a recurring theme. If I take the sort of infinite directed graph, where I have just a series of vertices, an infinite number of vertices extending out in both directions, and I just have directed arrows, then the symmetries of this thing, well, all I can do is shift it by a certain amount. Again, we'll treat that in greater detail later. Another theme we've discussed is that given a group, there are a whole bunch of other groups that sort of come out of that group. So making new groups out of old. And you should really think of this as being a very familiar sort of procedure. You've seen this sort of thing in great detail in linear algebra. You've seen subspaces of a given vector space, and that's the sort of thing that we saw with subgroups being part of a group. We saw things like the cyclic subgroup generated by an element. Well, that's sort of like having the vector space generated by a single vector. And there'll be a few other things that we'll see later in the course, like products of spaces corresponding or being analogous to products of groups. And then finally, something that I'll start talking about today. We know that stuff like Hom Rn has a vector space structure on it. Well, likewise, given a group, the set of morphisms between G and itself that are bijective form a group. And so we have a lot of analogies, and whenever you want to think about what's going on here, you can often think back. You can often use a lot of your intuitions from linear algebra. A third theme that we've looked at is that in some cases you can actually classify the subgroups of a given group. So last time we considered the subgroups of Z. Now, the argument we used to show that every subgroup of Z is of the form BZ looked innocuous, but it's actually a very significant argument. Again, it's something that's going to come back to haunt us, so it's a very good idea to familiarize yourself well with that argument. Just recall that basically what we did is we took a subgroup, we said, well, if it's non-zero, then there must be some smallest positive integer in it. And then we showed, using the Euclidean algorithm, that every element of the group must be a form of the form an integer times that smallest positive integer in the subgroup. So in general, though, it's very, very difficult to study the subgroup structure of a given group, but it's also very, very important. And then another thing that we looked at was particular cyclic subgroups. So I'll just refresh your memory on that. So if I have a group and I have an element of that group, I can consider the set of all powers of that element, and that forms a subgroup. So here are a couple of examples. If I take in GLNR, the element 1101, then, sorry, GL2R, thank you very much, N is 2. The cyclic subgroup generated by this thing, well, it's not hard to see that the powers of this thing all look like 1, N, 0, 1. This you can prove easily by induction, for instance. People who aren't familiar with mathematical induction maybe should see me after class. So this is ranging over all integers. So these are a lot of the sorts of themes we've seen so far. And so when you have infinitely many elements in the cyclic subgroup generated by a given element, you say that that element has infinite order. Of course, quite often, elements will not have infinite order. Quite often, there will be just finitely many distinct powers of something. For instance, if I just take, again, in GL2R, minus the identity matrix, then this thing has order 2. I square it, and I get the identity matrix.